Yeah. They don't get specifically, but not their watch bullets. It's like they're like anything else going on. I'll be like very pull up the shit. Get from your drink. It's all.
It's fun.
So that open ones are like Dune. It's like Dune. It's like
Guess we're good. Yeah.
Okay. Hello, everybody. We are having a workshop with Helius. Thank you, Evan, for joining us. We're going to talk about landing transactions, and Evan will tell you more about that, as well as the redacted cohack that we are having here today at the Toronto Vibe Station with Super Team Canada and Helius. And yeah, why don't you tell us about the cohack and then jump in?
Sweet, yeah. I mean, we're hosting a hackathon right now, so it's called the Redacted Hackathon, and basically it's just anybody interested in researching or sleuthing, getting to the bottom of just presenting on-chain data rather nicely. We're offering a bunch of money, so there are a bunch of different tracks. You can check it on the Super Team Earn site. So anything from looking into MEV bots or just researching sandwiches and whatnot. So highly recommend you check it out. A lot of big names on there like Dune, Arkham, and so forth. So yeah. But anyways, welcome. So this is Landing Transactions with Solana Web3.js 2.0. So my name is Evan, but online I go by the pseudonym Ichigo. I'm a developer experience engineer at Helius and have been for over a year now, so making me a seasoned veteran in the Solana trenches. I've become the resident blog guy, so I've written about anything and everything from Fire Dancer and zero knowledge proofs to our tendency to just blindly worship tech bros. I'm also currently working on a new Block Explorer orb, which should be live hopefully next week, fingers crossed. But yeah, it's the perfect role. I'm researching, writing, constantly coding, so anybody nerds. But I'm here today to talk about transactions because transactions are the lifeblood of any blockchain. You know, it doesn't matter if you're trading rare whiskeys, real estate perpetuals, or simply sending money to other people. It's all done through transactions. And so at Helius, we've had a renowned focus on improving our transaction flow, so much so that we've become the #1 provider with respect to landing rates. We've put out numerous guides, updated our docs, optimized and streamlined those transactions through our SDKs. And this isn't actually my first talk talking about transactions. But regardless of that, people are still having issues landing transactions. So the ultimate question today that we're going to answer is, how can we land transactions as fast as possible? So this talk, we're going to look at how we can land transactions effectively on Solana. So first, we're going to start with the fundamentals, so we're all on the same page and have a common understanding that we can just build off of. Next, we are going to explore proven strategies for reliable transaction landing. And then after that, we're going to implement everything using the new 2.0 release of Solana Web3.js. And so, what are transactions? A transaction is a set of instructions that interacts with a number of programs to modify on-chain data. And an instruction is a directive for a single invocation for a given program. So it basically says to the runtime what actions should be performed on what accounts and whether they have the necessary permissions to do so. And the important thing to note is instructions are processed in order, so it's sequential. So if the first thing in your transaction is a swap, it will always be a swap. If you're setting priority fees, which I highly recommend be one of the first instructions, that will execute first. And note that transactions are atomic, meaning the entire thing either runs or fails. So if one instruction along the way fails, then the entire transaction fails. And note that a transaction consists of 3 main parts. you have an array of accounts to read or write from. You have one or more signatures and one or more instructions. So transactions incur two types of fees. You have your base fee, which is a fixed fee of 5,000 LAMP ports, and that's per signature. And note that most transactions only have a single signature. And then you also have priority fees. So this is an optional, well, I say optional, but it's an optional fee that users can use to prioritize their transactions. So the base fee is there to compensate validators for processing transactions, and it introduces a real-time cost, whereas priority fees are instead there to incentivize users to boost their transaction priority. And this is helpful for time-sensitive transactions, high-value transactions, complex DeFi transactions. And since the 1.18 Agave update, transactions have been incentivized to use network resources a lot more efficiently because now the prioritization formula considers both transaction fees and resource costs. But we also have another kind of fee that's very popular, and those are Jito tips. So Jito is the leading MEV infra company on Solana. They host out-of-protocol block space auctions for partial rather than full blocks. And so instead of competing directly on-chain, users can participate in these off-chain auctions. It results in about a 200 millisecond speed bump for the whole auction process. But with that, you introduce guaranteed transaction inclusion. And so the process is as follows. So you have users, which are called searchers. They bundle a bunch of transactions together, anywhere between 1 to 5, and they submit them to Jito with a tip. And the minimum tip is 1,000 LAMP ports, and that's there just to prevent spam. And so block builders will compete to win these bundles, and then the winning bundles are guaranteed execution in the next block in order, all or nothing. And this is useful because you get guaranteed transaction inclusion. And it's, again, critical for a lot of the same reasons why priority fees are interesting. So for your complex DeFi transactions, anything MEV market related, time-sensitive transactions, high-value transactions, you can guarantee that those transactions will be executed in the next block. And of course, this opens up a number of MEV opportunities, arbitrage, because now you can secure specific transaction order. But note that this is different from the base fees and priority fees that I talked about earlier, because these tips actually go to block builders and not the validators themselves. And so that's just to incentivize the block builders to include those transactions in the next block. All transactions generally follow the same life cycle on Solana. So you have your transaction creation, your propagation, your validation, execution, and then confirmation. So transaction creation, you have a user who defines a goal, such as wanting to send 10 SOL from account A to account B. That user will then create a transaction specifying this action, and it will include the relevant accounts, instructions, and signatures. And then the transaction is sent to the network via an RPC provider like Helius. And then in terms of propagation, it's important to note that Solana has a mempool-less architecture, and its leader schedule is also deterministic. And because of that, this means that we can send transactions directly to the current leader, as well as the next few leaders. And note that transactions are transmitted using Quick for efficient and reliable transmission. And so you have your validation. So this is when the current leader actually receives, pre-processes, and validates the transaction. This includes checking its integrity, the relevant signatures, and ensuring it has enough fees to actually execute. And so when it does execute, transactions are ordered based on priority fees, compute requirements, all the other associated fees, and account locks. And that happens in the banking stage. And higher priority transactions are executed first, updating the blockchain state. And for confirmation, transactions and all of the updated state is then propagated throughout the network for confirmation by other validators via Turbine. And transactions are considered confirmed once a sufficient amount of validators, 2/3, have agreed upon the new state, and thus we finally complete the transaction lifecycle. So that's a lot of steps. And because of that, there are a number of potential reasons why transactions can actually fail along the way. And these failures, we can kind of categorize them into the same parts we delineated earlier with the creation, validation, and whatnot. But in terms of transaction creation failures, this includes things like invalid signatures. So transactions created with an invalid signature or without a signature at all will fail. This also includes instruction errors. So if you're creating a transaction and the instruction requires you pass in 5 mandatory accounts, you only pass in 1, the transaction will fail upon creation. Then we also have propagation failures, which includes things like network congestion. So despite how robust Quick can be, any sort of network delays there can cause transactions to drop, or you can experience packet loss. This also feeds into leader availability. So transactions might face delays if the leader is not available to actually receive these transactions, or if for whatever reason these transactions can't be forwarded to them directly. And this also plays into leader scheduling and validation failures. So if the current leader is overwhelmed, transactions may not be processed and will be dropped without ever actually failing on chain. And if you do get on chain, you have a number of execution failures. So this includes things like exceeding the compute budget. So transactions that consume more compute units than actually allocated will fail. And you also run into program errors. So any sort of execution errors or exceptions within the actual programs that are being invoked by the transaction, this can cause them to fail during execution. And lastly, it's a bit more rare, but in terms of confirmation failures, especially now that we're kind of going into a multi-client world with Agave and FireDancer and everything else in the works, it is possible to have inconsistent network state. So differing validator views of state, whether that be due to client-side or consensus bugs, may actually lead to inconsistent confirmations, or at the worst case, transaction reversions. Needless to say, there are many, many potential points for a transaction to fail. And blockchains live and breathe transactions. Of course, we should not have this many potential points of failure. Developers should just be able to send a transaction, know it will land, and not deal with any of the additional headaches. However, achieving this proves to be quite difficult. And optimizing Solana's transaction flow is an ongoing journey that requires continuous research, development, and collaboration within the ecosystem. Needless to say, we're working on it. And at Helius, we've been able to identify several key best practices that help and dramatically reduce the chances of transaction failure. So despite all these quirks and potential points of failure, how can I land transactions effectively today on Solana? So at a high level, you're going to want to implement the following best practices to land transactions effectively. So first, you want to use state connections to send your transactions. Add priority fees and calculate them dynamically. You want to optimize your compute CU usage. You want to skip pre-flight by setting skip pre-flight to true. You want to set max retries to 0 and implement your own robust client-side retry logic. You want to use a commitment of processed or confirmed, ideally confirmed, to fetch the latest block hash and for polling and sending and whatnot. And you can also consider using durable nonces if you need more granular execution control, as well as consider adding a Jito tip. So diving in, talking about stake connections, the first thing we actually need to talk about is stake-weighted quality of service. And so stake-weighted quality of service is a mechanism that prioritizes network traffic based on the stake that's held by validators. So this ensures that validators can send transactions more effectively, thereby enhancing their service quality. So Solana uses stake, so that is the funds locked up by a validator to secure the network, to signal how trustworthy a given validator is. So the idea is that these high-stake validators have a vested interest in the security and reliability of the network. And so Solana gives these stake validators more reliable performance when sending transactions by routing them through prioritized connections. And it's these prioritized connections which we refer to as staked connections. So as I mentioned earlier, unlike other blockchains, Solana doesn't have a mempool where transactions just sit and wait around before being processed. Instead, transactions are routed directly to the current leader and are processed by their TPU, or their transaction processing unit. So users create transactions, they submit them to RPC nodes via the JSON RPC API, and these nodes are acting as intermediaries between the users and the validators. And the important thing here to note is that RPC nodes are unstaked, non-voting, and therefore non-consensus. And so the connections are made from the RPC node to the validator using Quick again. And there are two types of connections. You have 500 open connections, which are accessible to any staked node, or sorry, any RPC node. And then you have 2,000 stake-weighted connections, which are only accessible to staked validators. And the idea here is that validators will get a share of these connections proportional to their total stake. So for an RPC to relay a transaction effectively, it therefore must be paired with a stake validator. And as I mentioned, since RPCs don't have stake themselves, it's on the validators to extend the stake virtually to the RPCs. And this is pretty much done with a stake node's overrides flag and a YAML file. And that YAML file will map an RPC identity to a value in LAM ports. And basically that value there represents if that RPC was a validator staked with that many LAM ports, we're going to give them stake connections proportional to that. And so the life cycle of transactions under stake-weighted quality service, as I talked about before, remains largely the same, except the only real difference is that transactions are sent via stake connections. And this means that they have better access to the current leader, drastically reducing the likelihood of delays or transactions being dropped, and so they never actually land on the chain. And we can think of stake connections like a toll road, where validators with more stake have access to less congested pathways, kind of akin to more lanes on the highway. In Colorado, for example, drivers can sit in traffic, or they can pay a few extra dollars and go through toll lanes. So express lanes are Colorado's network of premium lanes. And so similar to stake connections, basically they're both prioritized pathways to kind of reduce congestion for, like, quote, premium users. But we also need to be careful because this isn't the same thing as priority fees. And the common analogy of a toll road that a lot of people like to use, I mean, I'm guilty of it myself using it now, but it has the potential to blur the distinction between the two concepts. So priority fees come into play during the banking stage. And this is where leaders prioritize transactions based on things like the fees paid. So the general idea is that transactions willing to pay more should have higher priority and be executed first. Whereas stake-weighted quality of service, it only provides the connection access from the RPC to the validator. And it has nothing to do and does not affect in any way the prioritization that actually happens within the leader's transaction queue. It simply reduces the likelihood of transactions being delayed or dropped, so it can actually get to the leader and then. But before talking about priority fees, we should take a step back and quickly go however Solana actually processes these transactions. So there are a few key stages that transactions go through when the leader actually receives them. So first you have the fetch stage. So this is all under the transaction processing unit, the TPU I mentioned earlier. And the fetch stage is where transactions are received and batched from clients. And this is all done through dedicated sockets. So you have one socket which is dedicated to, I'll say, regular incoming transactions. Then you have one for vote transactions specifically. And then there's another one for all of the unprocessed transactions that were actually forwarded from the previous leader. So when you're the leader, because we have a deterministic leader schedule, if you know in the next 2 seconds I'm no longer going to be the leader, you're going to take all the transactions that you have in your queue and go to the next leader and say, hey, I can't process all these. I'm just going to forward them to you for processing. Then we also have the SIG verify stage. So this is where transactions are validated, all done in parallel using ED25519, which is simply just the cryptographic signature scheme that Solana uses. And then we have the banking stage where we'll kind of stop, because this is where transaction execution is handled using the central scheduler. And the banking stage is particularly important to understand when we want to talk about things like priority fees and prioritization. So the central scheduler is what actually manages prioritization and processing. And this is done through a sophisticated priority queue and dependency graph system. So in a nutshell, you have a central scheduling thread, which receives all incoming transactions from SigVerify. It then creates a prio graph, which is a directed acyclic graph. And what that does is track all the different transaction dependencies. And then transactions are organized into non-conflicting batches for parallel processing. And then the scheduler will then process the highest priority transactions while managing all of these dependencies. And so this is what a transaction dependency graph looks like. And we can interpret the arrows as meaning is dependent on. So for example, transaction A is dependent on by transaction B. Transaction B is dependent on by both transactions C and D. And looking at it, we can see that transaction A and E have the highest priority within their respective chain of dependencies. And obviously they don't conflict. So the scheduler will then move from left to right processing these transactions in batches. So you can see at the top there, the first batch is A and E. The second batch is B and F. The third batch is C, D, and G. And the fourth batch is H. And so basically what the scheduler is doing here is it identifies the transactions in descending order of priority, identifying all these conflicts, which is why they're in separate chains, and creates all those edges to represent dependencies. And it just moves across the line, processing them in order. And this ensures consistent priority handling across all transactions. It's done to minimize processing delays available and results in a more efficient compute unit management than, say, what we had a couple months ago, or especially what we had a year ago. And the scheduling system is what makes priority fees both possible and powerful. It provides the infrastructure for transactions to effectively compete for that earlier execution. And so, given this priority-based scheduling system, priority fees are a natural extension that let transactions influence their position within that queue with the central scheduler, the banking stage, and so forth. This is an optional fee developers can add to boost their transaction priority. I mean, I say optional with air quotes. It's becoming very commonplace nowadays just to land transactions in general. But the idea is that any sort of time-sensitive, high-value, or complex transactions should have sufficient priority fees to ensure they actually get executed on-chain. And the important thing to note here is that the fees scale with compute units. So this means that the more compute-intensive transactions need higher fees to maintain a higher priority. And since these fees vary based on things like account access, compute units needed, how hot these accounts are, and various other factors, it is highly recommended that you are setting these priority fees dynamically. Because if you set the priority fee to some obscenely high value, you run the risk of overpaying for your transactions. And if you set them too low, obviously this is going to hurt transaction landing rates, as these transactions won't actually land and be executed. And at Helius, we have a priority fee API, which exposes the get priority fee estimate RPC method. And that will provide fee recommendations based on historical data, as well as global and local fee markets. So basically, a developer can take a serialized signed transaction or pass in an array of accounts that their desired transaction would like to interact with. And the priority fee API will then spit out the appropriate fees for you to attach to that transaction and send off. And you can also pass in other things such as the transaction encoding. If you would like the transaction priority fees to be associated with a specific percentile, like if you want it above the 50% median fee, if you want the 75th percentile, and so forth. And you can also do other things, like if you wish to treat empty blocks as zero fee slots, or how many recent slots you actually want to use within that priority calculation, and so forth. And so optimizing compute units is crucial for effective priority calculations and setting priority fees because they directly impact transaction costs. And so we can define priority its calculation as fees divided by cost plus 1. And this is where fees is equal to priority fees multiplied by the compute units requested, and then plus the base fee. And then cost is the requested execution CUs, the signature CUs, and the write lock CUs all added together. And so in simpler terms, basically what we're doing is we are taking the transaction fees and we're dividing by the total resource consumption. And the plus 1 is just there to prevent any sort of division by 0. And this comprehensive cost calculation is there to kind of reflect the true resource cost of a transaction. And this carries 2 key implications for developers. So transactions requesting fewer compute units will actually receive a higher priority for the same fee. So the idea is that if you have 2 identical transactions, both consuming, say, 100,000 compute units, if the first one is not requesting any compute units, it will just default to requesting 200,000 CUs. But the second transaction, completely identical, if we request, say, 150,000 or 120,000, because it's requesting closer to its actual usage, it will get higher priority. And yeah, so very important to keep in mind. And so we can optimize our transactions priority by accurately estimating and requesting those compute units then. And developers can do this by simulating a transaction before actually sending it off. So Solana has a very handy simulate transaction RPC method, which, as the name implies, will simulate your transaction and then return relevant information such as what the log messages were, whether the simulation actually was successful or failed. But more importantly, for our purposes, it'll spit out the number of compute units that were consumed during the processing of that transaction. So we can take that value, we can add a very tiny buffer, create a compute budget instruction for our original transaction, and then use that value before we're sending off the transaction to actually request that many CUs. And as a quick aside, you can really go down a rabbit hole with different CU optimizations. So for example, there's a relatively new set loaded accounts data size limit instruction, which offers a powerful way to actually optimize CUs. So by default, Solana will actually load in 64 megabytes of account data. And this costs about 8 CUs per 32,000 kilobytes. So that means you're wasting upwards to maybe 16,000 CUs per given transaction. And so what the set loaded accounts data size limit does, it allows you to specify exactly how much account data you need loaded in for your transaction. So for example, if I only need 10 megabytes, I can use the set loaded accounts data size limit instruction to actually request and load in those 10 megabytes of account data. And instead of the default 64, we're actually going to be saving roughly 13,500 CUs, which is pretty good. And this can become quite powerful when you have very predictable account data needs. So if you are a wallet provider or a DeFi application or anything MEV related or market making where you're interacting with the same accounts over and over and over again, you can add this in and make your transactions more efficient. But of course, if that wasn't enough, we can really increase bandwidth and reduce latency and look into CU optimizations such as CU golfing. So CU golfing is basically the practice of writing or rewriting your program to use the least amount of CUs as possible. So any transaction that actually interacts with your program won't be as compute intensive. And this is basically the equivalent to gas golfing on Ethereum. So you'll see a lot of people using assembly or Yule, writing these crazy contracts for just very simple sends. That's all done to kind of reduce transaction costs. And so now the equivalent is becoming popular on Solana with the emergence of things like P token and Pinocchio. So here are a very, very few quick tips for actually reducing CUs. So if you're building a program, you want to be careful with your log messages. So log messages are obviously very helpful for debugging purposes, but if you leave them in and actually deploy your program, those instructions, which have an abundance of log messages, can be very, very expensive. And especially if you're doing stuff such as base 58 encoding within those logs or any sort of string hashing. You also want to choose the proper data type. So smaller data types actually consume fewer CUs. So for example, if you're using a vector of U8s compared to a vector of U64s, you can actually cut your compute unit usage by nearly 50% for any comparable operations. You also want to be careful with how you handle serialization and deserialization. So if you're using Borscht, this will obviously be a lot more almost prohibitively expensive compared to things like zero copy. And lastly, you want to optimize your PDA handling. So if you're using find program address to find your PDAs, it can be quite expensive. Instead, what you want to do is save your bumps and then use a create program address. And this will reduce your CUs from about 12K to roughly 1.6K. And these optimizations, they sound like they not be saving a lot, but they can add up very, very quickly. So you want to keep these in mind because transactions, you can fit a lot more of them per block if your program isn't requesting as many CUs for a given instruction. And to measure CUs for a given code snippet, you can basically just wrap whatever your desired code snippet is in the compute_fn macro. And that will tell you how many CUs that given code snippet is using. But anyways, back to the meat and bones of actually sending transactions. The send transaction RPC method conveniently has a number of optional config params that you can set in a certain way to actually speed up your transactions. So the first thing is pre-flight. So you want to set your skip pre-flight checks to true. And what this will do is skip pre-flight transaction checks. And so what are they? This includes things such as simulation and signature verification, just to make sure everything's all good. But if you skip those checks, you can save about 100 milliseconds in your transaction sending flow. So if you're confident that you're sending valid transactions, you can safely skip these checks. Also, max retries. So it's recommended to set max retries. So that is the number of times for the RPC to actually retry the transaction on your behalf to 0. And instead, what you should be doing is implement a custom client-side retry logic. So this can allow for more effective rebroadcasting, say every 1 to 2 seconds. And basically, it avoids any sort of transaction queue on the RPC side. And in terms of commitment levels, the commitment level you're using can have a significant impact on your app and your transaction speed. So for example, you can simply speed up your app by 10x if you change any finalized commitments to confirmed. And the important thing to note here is that no confirmed block has ever not been finalized in the past 5 years of Solana. So if you're scared about changing from finalized to confirmed, so far so good. And you could take this a step further. So if you're fetching your block hash, for example, you could, instead of using a confirmed commitment level, go down to a processed commitment level. A lot of people argue it's sufficient for most use cases. It reduces the chance of that block hash actually expiring. However, it's very, very risky as a transaction using that commitment level could land in a block that's actually forked off. And so for that reason, I'd highly recommend you use confirmed for most cases. And you could use finalized if you have some life or death transaction that's going to stop a hack, save $1 million or whatever, or you just want those extra guarantees, you could use finalized. But regardless of whether you pick confirmed, finalized, or whatnot, you want to make sure that your entire app is using the same commitment level. And this is just done to ensure consistency within your app's behavior. You don't want to send a transaction if the block hash was using a process commitment level, the send transaction has a confirmed commitment level, and then your polling has a finalized commitment level. It's way better for consistency if you just have the same level all throughout. Durable nonces are one of the more controversial topics, as you may see on crypto Twitter. But they can be a powerful alternative to using a recent block hash to sign a transaction. So unlike regular transactions, which expire after 150 blocks or about 90 seconds, durable nonce transactions actually don't have an expiration date. So the idea is that you create a nonce account that holds both an authority and a nonce value. So the nonce value is what's actually replacing that recent block hash in the transaction. And a transaction that uses a nonce value must start with an advanced nonce instruction. and the nonce authority must also be the one signing the transaction. And once used, that specific nonce cannot be used again. And this makes durable nonces extremely useful for a variety of use cases. For example, you have fee optimization. So what you could do is generate multiple versions of a single transaction. So you have your base transaction, and then the first version of that is sent off using 1/10 of the median fee. We'll wait a second, see if it's confirmed. If not, we'll send that same transaction except with 1/4 of the median fee. Wait a second, if it's still not confirmed, we can then send it with half the median fee and so forth. So the interesting thing about that is you're only going to be paying for the transaction that actually lands, because that nonce will invalidate all the other ones once it lands. And you could potentially send multiple transactions to multiple RPCs. Please don't spam us. You'll find that Helius has the highest landing rates anyway, so just send a well-optimized transaction there. But if you do have some sort of existential, life or death transaction that absolutely have to land, you could technically use durable nonces to send it to multiple providers. And again, the interesting about that is you're guaranteeing execution, and because you're using a durable nonce, that nonce value, you can ensure that only one of those transactions is actually going to land. And so this kind of all bleeds into execution control. So what we're referring to when we advance the nonce, what we're saying is that, hey, we're going to take the nonce value and we'll increment it. And so this is why every transaction that uses a nonce value has to have that advanced nonce instruction. So we could send a transaction with the nonce value it's 1, the second one is the nonce value 2, the third one, the nonce value 3, and so forth. And basically, this is what enables that use once property. And it gives you a lot more control over the execution window, because you could basically cancel pending transactions by sending another one. And this is a lot nicer than, say, transferring funds from one account to another to actually block the execution. And then, as mentioned earlier, Jito tips are a very popular fee option for landing transactions on Solana because it introduces that guaranteed transaction execution. However, we need to point out that not every transaction needs a very, very big Jito tip. Jito is excellent for landing transactions at the top of the block, so it's the first one being executed. But the average user doesn't necessarily need this. If you're interacting with a Helium hotspot, doing a simple transfer, or say upgrading a gaming NFT, you don't need your transaction to land at the top of the block. We're finding that users will often have more success with a well-optimized transaction that's routed through state connections. But if you are looking to do anything MEV or market making related, or any sort of trading, if you're relatively price insensitive, and you need those execution guarantees for specific transaction ordering and whatnot, use Jito tips. However, if that doesn't really apply to you, just keep in mind that having a huge tip is not 100% necessary. And so combining these optimizations will have a compounding effect. Bar the durable nonces and Jito tips, you don't want to just implement one of these best practices. You want to be implementing all of them. And that will then give you the best transaction flow possible. Okay, cool. So how do I actually implement them? So today we will be looking into the new upcoming 2.0 release of Solana Web3.js, which has been renamed Solana Kit. And it's basically a significant modernization of how you would traditionally interact with Solana using JavaScript and TypeScript. It's a completely new API that breaks any sort of compatibility with any 1.x versions, but it's done so for good reason. And we can break down why this release is particularly exciting. So the first thing is we're seeing major improvements in bundle size and loading times. So because 2.0 is actually tree shakeable, this means that you only bundle and import what you actually use instead of the entire package. It also introduces enhanced type safety, which is particularly important when you're trying to do something complex in Solana. So you will potentially catch errors during development rather than at runtime. And 2.0 also fully embraces modern JavaScript features such as native async await patterns, better error handling, and it includes native TypeScript support out of the box. And ultimately, this makes your code cleaner and more maintainable. And it also introduces this enhanced flexibility where you can do a lot more things compared to any sort of the 1.0 versions. So for example, you have much more control how you interact with Solana because you can customize RPC implementations, implement your own transaction signing mechanisms, or you can even create your own specialized network transports. And yes, the names are actually that long. Well, it's quite a mouthful. It's a move towards a more explicit self-documenting API. Don't worry, I have asked, and they are open to reducing these names. However, the argument is in the age of AI, intelligence, vibe coding, auto-completion, it's arguably these more descriptive names that could make our code more maintainable and easier to understand. Nice. So let's actually see some code. So I have a very, very simple transaction sending script here. You'll notice compared to 1.0 that we are importing a lot more stuff from Web3.js. We then also are making imports directly from the system program as well as the compute budget program. So this includes things like error messages, a simple get sol transfer instruction, and then all of this is the compute unit limits and whatnot. A bit more imports, handy.env, so I'm not leaking my API keys or private keys or anything. And so here we have the initial setup. So we have our Helius RPC URL, and then we have a create Solana RPC that we're using. And basically this function here establishes communication with the RPC server using the default HTTP transport. And that's sufficient for most use cases. But you'll also notice that we have an RPC subscriptions variable here. And so create Solana RPC subscriptions, basically what that does is it establishes a WebSocket connection. So if you're doing anything that you'd need to pull, for example, pulling a transaction's confirmation status, then you're going to need the WebSocket connection there. Then we have a very basic key pair signer and 2 public key that we're just setting up there, and we'll log it for testing purposes. Then what we're going to do is fetch the latest block hash. So we can then use the RPC variable that we create up here with create Solana RPC to then fetch the latest block hash. Note that we're using the confirmed commitment level here, and then we'll just send that off and wait for it to come back. Then we're going to create a very basic transfer instruction using the get transfer sol instruction. So this takes an amount, a destination, and a source. So the amount we're going to do here, you'll notice, is not just a regular int, but it's a big int. So that's one of the bigger changes. And we can wrap that in the lamports function that we imported up top. And we're basically going to say, all right, we're sending 1,000,000 lamports to the 2 public key, and that's going to come from our key pair signer. And so if we want to be an account data optimizer, we could use the loaded accounts data size limit instruction. So basically here, I'm just saying, hey, I don't want to take in the full 64 megabytes. We'll try and shorten it a bit with a 32 kilobyte limit. Then the interesting part here is how we create the transaction message. It's a bit different and uses a pipe function. So the pipe function is commonly used in functional programming. And basically what it does is it creates a sequence of functions where the output of one becomes the input of next. So here we create the transaction message using version 0. And then the output of whatever's created here will then take as tx. And with an arrow function, we'll modify it and we'll set the fee pair. And so yeah, basically we're taking that newly constructed transaction message, and each time we are passing it in over and over and over to create new messages, setting things like the block hash. We're going to add the account data instruction as well as the transfer instruction. And then here we're going to want to get the priority fee estimate. So we're signing the transaction and using it as encoding it as base64. And then we are doing a nice post request to the aforementioned get priority fee estimate. You could use the Helius SDK to kind of streamline this, but just for testing purposes, if you don't want to use the SDK, this is how you would pass it in. So under our params, we're passing in the base64 encoded transaction. We're specifying that our transaction encoding is base64. And the recommended param here is basically saying, hey, I just want my transaction to be above the recommended fee, which is like the 50th percentile. I don't really care for, if I want like a really, really high transaction fee. All I want is the recommended just for testing purposes. And so we'll send it off and we'll await the response. And then from there, we can take the priority fee estimate and then we will log it just for testing purposes. And then after that, we're going to get the compute unit estimate. So here we have one of the longer function names, the get compute unit estimate for transaction message factory. And basically what we're creating here is a reusable function that we can just call over and over and over again with different transaction messages to actually get the compute units. And what we're doing here is we'll take whatever is returned from the compute units and we'll basically say, hey, if it's less than 1,000, we'll set 1,000 as kind of like the lower threshold, or we will take the compute units and add a small buffer of 10%. And basically that's because some of the smaller transactions historically have been having issues landing. So if you just set a lower threshold of 1,000, you're pretty good. And if not, we're adding a 10% buffer. And the reason for that is the buffer kind of accounts for compute units used by the priority fee instructions. Obviously, we could just add those on. However, if you're doing a bit more complex stuff on Solana, for example, if you are doing a swap and you have a simulated route, the route could change by the time from simulation to actual execution. So if you're requesting the exact number of CUs within the simulation, it is possible that the route changes and then it adds 1 or 2 extra hops and then your transaction actually fails. So that 10% buffer is just kind of a fail-safe and we'll log that out. And then finally, we're going to create the final transaction that will actually be sending off. And so we'll fetch the block hash again, so it's just a bit more recent. We'll set the commitment level to confirmed. And then what we're going to do is we're actually going to prepend the transaction message with our compute unit price and compute unit limit instructions. And the reason we're prepending is because we want those to be the first instructions within the transaction. And so they execute first, because as mentioned, instructions are executed sequentially and in order. So we don't want to send and then set the priority fees, then set the compute unit. We want to make sure that's all set first and then actually do what we want to do. Because you could come into issues where, say, you use a bunch of compute units at the start and then it fails, and then you have your instruction that actually sets the compute unit limit. So if you bump that up first, you run into less issues of actually exceeding the compute unit budget. And then here, basically the next part here is just sending off the transaction. The catch here, this is just because we are skipping pre-flight transaction checks. So this is a bit more of a nicer debugging error process just for testing purposes. Because within the try, we take the transaction, we sign it, and then we create a send and confirm transaction factory, passing in the RPC and the RPC subscriptions. And then using that, we will send and confirm the transaction finally. And so we'll take the finally signed transaction and we'll set the commitment level at confirmed, max retries to 0, and then skip pre-flight checks. And so that's why we have the nice error handling here in case I create a bogus transaction that's not actually valid and it doesn't run. And so here we can actually run it. And then we can see we have the from, the to, the priority fee, the compute units, and then the transaction was confirmed. So if we take the transaction signature, go into our handy dandy Helius Block Explorer. We can see it was a transfer. It was successful. And down here, we are consuming 600 CUs. So the 1,000 was pretty close. And we are setting the compute unit price, the compute unit limit. We also have that set loaded accounts data size limit instruction. And then we have our simple transfer. We can also look at another quick example. So sending through Jito. And so the setup is very similar. We have all our nice imports. It's pretty much standard. Now here, you can streamline this with the Helius SDK or other SDKs, but we're taking in all the Jito tip accounts. And we're going to be using this later because, as mentioned before, Jito transactions have to have a Jito tip, and you send it off to one of these tip accounts. And the reason why I'm kind of pulling them all in is because we want to make the selection of that as random as possible. Because if you keep sending to the same tip accounts, you then start to compete with other people who are repeatedly sent and hitting the same tip accounts. And that's when you start getting into those account lock battles. So if we're all trying to read or all trying to write to the same account, obviously we won't be as successful. So we want to keep this as random as possible to increase our chances of actually landing successfully. The sending is a bit different because we're sending it to Jito. So we're making a post request to the Jito URL that we will pass in. And basically we're saying, hey, we're going to send the bundle. It's going to be a serialized transaction using base64 encoding. And if there's any errors, we'll catch them, throw them, and we'll know. And Jito is a bit different because we also need to get the status of the bundle. So the bundle, as I said, is that group of 1 to 5 transactions that's actually being executed. And we're using the get bundled statuses method. And again, if there's any sort of errors, we'll log them. So the Jito tip functionality will be using the Jito URL, which is the mainnet.block engine, basically sending to their bundles endpoint. Then we have that random tip count, where basically we're taking that array from earlier and we'll just pick a random count from one of those. And as again, that is done to avoid any sort of CU lockouts. And the tip, we're just going to send the bare minimum 1,000. Our initial setup is the same. We fetch the latest block hash using a confirm commitment level. So the first one is going to be our transfer instruction, same as before. And then we have our Jito tip instruction. So here we're passing in the tip amount as the amount. The destination will be that random tip account. And of course, we're going to be the one signing for it. The transaction message using the pipe is pretty much the same, except we have the transfer instruction as well as the tip instruction. We're going to get the priority fee estimate here, making another post request, just using the recommended priority fees. Then we'll estimate the compute unit usage, same as before. And then we'll take that final transaction and fetch the block hash one more time using a commitment level of confirmed. Prepend all of those compute unit price and compute unit limit instructions. And then it's a bit different because we actually have to handle the polling ourselves. So what we're going to do is we're going to sign the transaction, serialize it as a base64 encoded transaction. And what we need to do is then send the Jito bundle, and this will return a bundle ID. And I have a very simple polling configuration here just to look if the bundle is confirmed, because unfortunately we can't use like send and confirm as a method to send it off. So what we're going to do is we're going to get the current block height as well as calculate the last valid block height. So basically we're saying, hey, from now up until 150 blocks from now, when the block hash will expire, I kind of want to know that range. And here in the while loop, we're going to be doing that at the bottom, as well as I also set up a little timeout. So the timeout there is 60 seconds. So from now up until 60 seconds, if the transaction hasn't landed, Obviously, something has gone wrong because we're optimizing for CUs, priority fees, and Jito tip. So we need to investigate. But basically, within that time, we're just going to pull the status of the bundle. So if we can find a confirmation status, if it's equal to confirmed, which is the commitment level we've been using throughout, we're like, okay, cool, we confirm the transaction, this is the signature, and we'll return. If not, we'll keep pulling. And I also then have the nice debugging here for pre-flight checks. And so we can run this one as well. So we have the Jito bundle ID, and you'll notice it's taking a bit longer as we're actually waiting for the bundle to confirm. And the bundle has been confirmed. And so we have our signature, which we can then pop into our block explorer. We'll notice that the transfer was successful. The Jito tip account 4 is the one we picked. So you can also see here the optional Jito tip. It's that 1,000 lamp ports that we sent. And within the instructions, you see the set compute unit price, the compute unit limit, the transfer, as that Jito tip there. And you'll notice compared to the other simple send, this was a lot slower. And that's because it does have to go through that Jito process. And because we're doing something like a simple send and we're not really tipping that much, block builders aren't really that incentivized to include our transaction. So if you're doing something like a simple send, as I said, a well-optimized transaction through state connections will oftentimes be a lot faster than a transaction with a Jito tip. And yeah, thank you. If you have any questions, comments, concerns, want to talk, I'll be around. But yeah, thank you.
Awesome. Thank you so much. I'm sorry. Hi. All right. Thank you on behalf of Super Team Canada.
No worries. Thank you.
We had 188 viewers at the end of this session. It's pretty cool.
Not bad. Not bad.
Well done.
Well, thank you.
We have a question.
Are you going to share the presentation?
Yeah, I can share the slides, and if you guys want the code snippets as well, we can send it around. Yeah. We do also have an article on the Helius blog that kind of goes through the 2.0 sending process, so I can link that as well. But yeah, I'll make a gist on GitHub, and we can send it. My private key or anything, or API key, but it's yeah. There's not much on it anyway. It's just a simple testing, but yeah, for sure.
Awesome. So we have Vibe stations today in 3 cities across Canada: Toronto, which is where we are here, Montreal, and Vancouver. Shout out to the other Vibe stations that are watching this stream. Thanks for joining us. Yeah. So we're here every Friday from 10 a.m. until 7 p.m. Come on out and join us. You can find it on Luma, on the Super Team Can calendar. Follow us on Twitter, and the redacted co-hack with Helius is ongoing, so check that out on the Helius Twitter page. And yeah, thanks for joining us.
Thank you.
Really
Appreciate it. Thank you, guys.
All right. Thanks.
Yeah.
Oh, should probably just